pizza steak. I just have a few slides about some of the chemistry that we have going on in our lab. I've only been working in the lab at Kennesaw for going on my second semester now. And so I'm going to show you more ideas and results that we have today. But have a lot of ideas, and we work in an area that not a lot of people work in, so we're looking at organophosphorus chemistry, and to outline a little bit of the chemistry, a little bit of the background for this. If you have any questions, just speak up. So I will show some chemical structures here in a moment, but I do a lot of synthetic methodology, and that means we look at chemical reactions and that might be reported in the literature, or we try to develop new chemical reactions and we try to improve upon those methods. Sometimes it's important because the methods might use environmentally unfriendly solvents, or they might be very expensive solvents, or the reagents may be expensive, the yields may be low of particular compounds. So we look at methods that we can improve the reactions and that we can get better outcomes. We can make more complicated derivatives so that they may have potential functional use, such as maybe drugs or agricultural products and things of that nature. So we target the chemistry, and then the long-term goal is to target compounds that we might make that have some industrial application. So we have a series of these organophosphorus compounds. They all are functionalized: carbamoyl, keto, hydroxy, which is alcohol, amino, and vinyl. And like I said, we were going to work on this. We're starting with this area, and the long-term goal is to do medicinal chemistry. And as we're going along, we're trying to look at urine chemistry. So we're trying to do chemical reactions in water, trying to get away from using solvents, using things like ultrasound to promote reactions so you don't have to use heat, and things that shorten reaction time. So let me give you just a little bit of a summary of some of the things that we're doing here. So here's just a generic slide that shows the chemical structure of these phosphonates. And so here with the carbamoyls, you just have an amido group attached to this phosphonate here. So a phosphonate is like an ester, a phosphorus ester, and then here you have an amide group beside the phosphorus ester. We're working a lot in the area of the ketophosphonates. You have the ketone functionality. And what's interesting about these molecules, you have this phosphorus site here that sometimes acts like an ester, and then sometimes this acts like an ester, so you can change the chemistry back and forth even though it has a ketone functionality. Sometimes you can displace the carbonyl side, sometimes you can displace the phosphorus side, depending on what reagents. But a lot of the chemistry we're working on, we're focusing on actually the carbonyl group to convert it to other groups. So we can convert the carbonyl group to, say, for the hydroxyphosphonates, or we can convert them into the aminophosphonates, we can convert them into the vinyl phosphonates. And so, for instance, in terms of use, the carbonyl phosphonates have a lot of interest because they've been discovered to have a lot of enzyme inhibitory activity. So there's been a lot of research and publishing, and a lot of patents and interest in the area. Ketophosphonates also have some biological activity, but they're oftentimes precursors. Hydroxyphosphonates will show you some structures of actual compounds that are being used today, and as well as the amino. And then the vinyl phosphonates have potential application in the polymer chemistry. You saw the one slide with Dr. Gabriel's molecules that are fire retardant. Well, they had a phosphonate group in them, so potentially we could build monomers and look at them and to build the polymers and functionalize polymers to see if they have particular fire retardant properties, or they even have antimicrobial properties. So there's a lot of chemistry and a lot of applications using these types of molecules. So I sort of already said why, but you may not recognize these drugs, but phosphomycin is, when you have your alpha hydroxy here, it's an epoxide, and it's a phosphonic acid form, but this is an antibiotic, and it's particularly used to treat urinary tract infections in women. And so that is an actual marketed drug. Cidofovir is an antiviral drug and on the market, and it's used to treat HIV infections, herpes infections, different types of hepatitis, and so has a wide range of uses. Phosphomax is made by Pfizer, and you might see advertisements sometimes on the TV for these lawsuits, and these attorneys are trying to sue for these different compounds because they have bad side effects. Well, this is the one that has a lot of attention around it. But it is actually a really nice compound because it's used to treat osteoporosis. And it's also used to treat bone pain related to cancer, to bone cancer, and it's also used to treat as an agent to treat metastatic breast cancer, which oftentimes ends up in the bones. And so it's also to treat another disease called Paget's disease. So all these are bone-related diseases, and so this is an important compound for here. So 3 drugs, and then here you might know this if you've ever worked in your yard or worked in a garden somewhere. You might have used some Roundup. So this is a broad-spectrum herbicide. You see advertisements on TV all the time for this. This was invented by Monsanto, so if you go to Lowe's or Home Depot, you can just buy this in big jugs. Very effective, but very simple molecule, and it has the alpha amino functionality. These 3 have the alpha hydroxy, and this one has an alpha amino. So these are examples here of current molecules that are industrially and pharmaceutically important for us. So a lot of my slides are just generic. As I said, I'm just starting out, so just kind of presenting some of the ideas. Now, this slide here is focusing on the ketophosphonate, and this is just a pinwheel of chemistries that have already been reported in the literature. So you can see a lot of these chemistries are all focused on the carbonyl. So they're doing all the chemistries that we would do for a normal ketone, but we're doing it in the presence of phosphorus, because sometimes that reactivity around that carbonyl group does not necessarily behave the same as it is for a ketone. So you can do all kinds of things. You can do enolate reactions, aldol reactions, Henry reactions. You can do chlorination. You can make double bonds using Wittig reactions. You can do oxidation with biovinegar. You can do organometallic 1,2 addition reactions at the carbonyl with things like Grignard reagents. Here we can make enol nonaphthalates or enol tosylates, and we can do organometallic chemistry to functionalize and make the vinyl phosphonates. And here we can make, here's an example here where we take an amine and we're able to displace the phosphorus group, and now we're making amides this way. And there's other derivatives as well that you can mix. So there's a lot of chemistry that's been reported, a lot of room for developing new chemistries or improved methods, and also studying the reactions and why some of these processes occur and why some of them do not. Here's a slide that is showing some current chemistry that we're working on. Very classical reaction here, this Michaelis-Abruzov reaction is the most common reaction to make ketophosphonates. Take an acid halide and